Thank you so much, and thank you everyone for joining us tonight. But most importantly, thank you for supporting all of our research. I often say organizations like yours that allow us scientists to think outside the box and try things that maybe federal funding would initially deem as too risky is something that you allow us to do, and that often leads to very, very promising results. So thank you for all your support. I'm going to briefly give you an overview of what we have been doing and continue to do, and what this year's funding is going to extend in terms of the research that we are doing. So our laboratory is focusing mostly on duplications as the second most common of Duchenne mutations. And they present a unique therapeutic challenge as they're, for example, not amenable to some of the antisense oligonucleotide therapies that you have heard about. So several years ago, we have developed a methodology using the CRISPR genetic scissors, how we call them, to remove with one guide the duplicated portion of mutation in the dystrophin gene. As you can see here, you can use one guide that cuts out a piece in the normal piece of dystrophin and in the abnormal piece of dystrophin, and then gives you a wild type, normal, fully functional dystrophin gene. And we have tried this in a duplicated mouse model of an exon 18 to 30 Duchenne model. And as you can see here in the middle, we were fairly successful in increasing the expression of what we call wild type dystrophin. This is full length dystrophin that's expressed, which is different than some of the gene therapy trials that are currently ongoing that use a smaller version of dystrophin. However, as you can see, while the expression looks promising, we were thinking about what could we do to further enhance the expression of dystrophin. And you can use the CRISPR system in two ways. The way how I just showed you, that you use a guide and you cut out the duplicated portion of the dystrophin gene. That gives you a full-length normal wild-type dystrophin gene. But you can also inactivate the scissors of the CRISPR-Cas9 machinery. And what you can do without the scissors is you can target what we call the promoter, which is kind of the area of the gene that forces the expression of the gene product. And you can enhance dystrophin expression that way. And that's exactly what we have done. So we had on one side the scissors, and on the other side a non-scissor CRISPR product that helps you to increase further the dystrophin expression. We did a proof of concept experiment where we injected this in just a single muscle right here. We waited 5 weeks, and we were quite excited to see that you can see here, if you just cut out the dystrophin duplication, you get a certain amount of dystrophin expression. But if you add on this non-cutting product of CRISPR-Cas9, you can actually increase the expression even further. So what I cannot show you quite yet, because we are still analyzing these mice, how this looks like if you give a systemic injection that would try to reach all muscles. So if we're going to have this wonderful event next year, I promise I'll show you how that looks like. Now, for this year's competition, what we are focusing on is trying to create a mouse model that would be really the closest possible model before we can go into a clinical trial. So what do I mean by that? When we are thinking about gene-correcting therapies, and we are trying to correct certain mutations in a mouse, while this is, as a proof of principle, quite important and necessary to demonstrate, as you can see here, there are certain portions within the dystrophin gene that are different between a mouse and between a human. So all the purple areas show you that there are differences, which shows you that whatever you do in a mouse may not be necessarily 100% translated into a human. So what we have tried to do, and successfully tried to do now, is to create a mouse that has a human copy of the dystrophin gene. Now, almost 20 years ago, a mouse like this was established in the Netherlands. And a couple of years ago, we figured out that this mouse is actually not kind of the human, doesn't really carry a human dystrophin gene the way that would allow us to do the experiments, because it actually had two copies of the gene, as you can see here. So what we had to do in order to create a mouse that would really provide us the opportunity to have a true preclinical model is we had to remove, with CRISPR-Cas9, the same way how we did this in the other mouse, this duplication, to then come up with one single copy of the human dystrophin gene in the mouse. And finally, after a lot of work, we have this mouse. It's a healthy mouse. So you're looking now at a healthy muscle of a mouse that carries one copy of the human dystrophin gene. And that now positions us extremely well to do lots of different experiments. We are going to create duplication mutations on this human part of the dystrophin gene. We're going to analyze these mice, and then obviously we are going to go back and try our CRISPR-Cas9 approach that I showed you before. Plus, we are going to do this in combination with either steroids or one of the newer drugs that you probably have heard about, vamorolone, which is a steroid-like drug that has a less side effects though. So we are really trying to create the most closest preclinical situation to humans. And we hope that if the results of these studies are going to give us what we anticipate to see, that we are able to then really think about how to start a clinical trial with these products. So thank you again. I want to just mention this young gentleman, Matthew Rock, who is doing most of the experiments, and a new graduate student, Lucy, who's going to continue some of the work. Thank you again for your support. We really couldn't do it all without you.